Hello there. In this video we're going to continue our discussion about linear functions. So recall, a linear function is any function of the form f of x is equal to mx plus b. Here m is typically referred to as the slope of the linear function and b is typically referred to as the vertical intercept. So vertical intercept of the linear function, and if we're talking about y's and x's, some people refer to as the y-intercept. So we're going to do a couple examples on how to construct particular linear functions that satisfy some properties, and we'll also discuss some additional properties of linear functions as well. Alright, so as our first example, so example 1, suppose we want a linear function, and let's call that a linear function f, such that, let's assume we want f of 2 to be equal to 5, and let's also assume that f of 4, we want that to be equal to, say, negative 12. So let's figure out the slope and the vertical intercept for a function f for which it is linear that satisfies these two properties. So what I'm going to do is I'm going to call this x1, y1, and this x2 and y2. So from these 2 points, then we can find the slope of that line. So we know that the slope, as we know, is the change in y divided by the change in x. So that's going to be equal to y2 minus y1 divided by x2 minus x1. So negative 12 minus 5 is going to be negative 17, and 4 minus 2 is going to be equal to 2. So the slope of our linear function is going to be negative 17 halves. So up to this stage, that means our linear function f is of the structure negative 17 halves x plus some constant b. So we need to figure out what this constant is equal to. So I'm going to pick any one of these points, and it doesn't really matter which point you choose. I'm going to choose that one because it doesn't have any negative numbers in it, but you should get the same exact answer if you were to choose the second point as well. So f of 2 must be equal to 5, so that means this must be equal to 5, must be equal to negative 17 halves times 2 plus our vertical intercept of b. By luck, the denominator and the number I'm multiplying are the same, so they will cancel. So I have that 5 must be equal to negative 17 plus b, which means my vertical intercept b must be equal to 17 plus 5, which we know is equal to 22. So combining all these things together, that means my linear function f of x is going to be equal to negative 17 halves x plus 22. So that is my linear function that I desire. So let's work through another example. Suppose we want another function g that satisfies g of negative 3 is equal to 7 and g of 1 is equal to negative 4. So again, I'm going to find the slope that passes through these 2 points. So I'm going to call it x1, y1, x2, and y2. As we know, the slope is given by delta y divided by delta x, which is going to be y2 minus y1 all over x2 minus x1. And I always suggest putting parentheses around these numbers just so that you do not get any negative things mixed up. So negative 4 minus 7 is going to be negative 11, and 1 minus negative 3 is the same as 1 plus 3, which is going to be 4. So this is going to be equal to negative 11 fourths as my slope. So with this being said, that means our linear function g is of the structure negative 11 fourths x plus some constant b, and our goal is to figure out, okay, what is this b equal to? I'm going to let's use this point as an example. So g must be equal to negative 4 when x is equal to 1. What b makes this true? So I'm going to add 11 fourths to both sides of this equation. So I get that b must be equal to 11 fourths minus 4. So I'm going to get a common denominator here, so that's going to be 11 minus 16, all divided by 4, which we know is going to be negative 5 fourths as my vertical intercept. So with this being said, our linear function that we desire is going to be equal to negative 11 fourths x minus 5/4. And that is the linear function that satisfies the two criteria that I wanted. And these are the more in-depth examples. If you want a particular slope or a particular vertical intercept, typically it's a little bit more easier because you already know one or two of the parameters of your interested linear function. All right, so in general, linear functions are ones of the form f of x is equal to mx plus b. So what is the domain of these types of functions? So since we have two operations here, we have a real number times some other real number that we do not know, plus some other real number, then since the set of real numbers is closed under, say, multiplication and addition, then we can say that the domain of linear function f is going to be equal to all real numbers. That is, no matter what real number you choose for x, n times that real number plus b, you can pretty much get a real number out, and you're not going to be divided by 0 or anything special like that. Also, consider the range of this function. So the range of this function is going to be equal to what? So we have a couple scenarios here. So we have positive slope going up, negative slope going down, horizontal line going that way, and vertical lines aren't functions. So the only case where the range does not span the entire set of real numbers is the horizontal line. So we actually have two cases for the range of linear functions. So the range of a linear function is going to be equal to the set of real numbers if the slope is non-equal to 0, and it's going to be equal to the vertical intercept because that's pretty much going to be the only y value for which it takes, and this is going to be true if the slope is equal to 0. So that is the domain and the range of linear functions in general in all the possible cases. And also, let's see if linear functions are one-to-one. So clearly you can see that if we draw any horizontal line for the m not equal to 0 case, then you should not have any issues in terms of one-to-oneness. So let's state a theorem. So all linear functions with the slope not being equal to 0 are 1, 2, 1. So let's see if we can construct a very formal proof of this. So what do I mean by a function is one-to-one? So in formal notation, that means for any y that we choose located in the range of our function, there exists a unique x in the domain of f such that f of x is equal to y. And if you're not familiar with this notation, that's pretty much how you read it. So for any y you choose in the range, so it has to be arbitrary, there exists a particular x in the domain, and it has to be a unique value. That's what this exclamation mark means. And it has to be in the domain, of course, such that f of x must be equal to y. So an example of a function that would not be one-to-one would be like x squared, because 2 squared is 4 and negative 2 squared is 4. So if you pick 4 in the range, there is not a unique x in the domain that corresponds to it, because 2 and negative 2 give you 4, but they're not the same. All right, let's see if we can prove this. So I'm going to let y be an element of the range of f, which we know, of course, is r. So it doesn't matter which number you choose instead of real numbers, there should be a unique x that corresponds to it. So since m is not equal to 0 by assumption of this theorem, then for some x in the domain of f, we have that f of x must be equal to mx plus b. And how do I know this is true? Well, that's just the definition of a linear function. And I know since the range of this is r, then that means there has to be some x that corresponds to the value of y. the y for which I have chosen. So what x value makes this equation true? So we can, show that it is a unique number that corresponds to this function. So I'm going to begin by subtracting both sides of this equation by b. So I have that mx must be equal to y minus b. And then I can divide both sides by m, since m is non-zero. So I have that my particular x value is going to be equal to y minus b divided by m. So that is my unique value. Unique value. For some particular chosen y and b and m are of course given by some linear function, and m is non-zero, so this is definitely well defined. So pretty much in this video we talked about a couple additional properties of linear functions, the domain of a linear function, the range of a linear function, the fact that non-horizontal lines are always one-to-one if you're in 2 dimensions, and we also did a couple examples on how to construct linear functions that satisfy a couple different characteristics that we desire.